Hi, welcome back. Today we're going to be talking about amplitude amplification, which is a generalization of the quantum search algorithm that we covered last time. In addition, I'm going to be showing you how you can combine this with phase estimation in order to be able to design an algorithm that can be used in order to estimate probabilities of different outcomes quadratically faster than what's possible classically. Finally, what I'm going to do is I'm going to show that Grover's search is optimal by presenting a proof technique known as the Polynomial Method that can be used in order to be able to prove lower bounds for both quantum as well as classical query complexity. So that's the outline of today's lecture. Let's get started. So, page. Okay, so amplitude amplification. The idea behind amplitude amplification is really, you can think of as just an elaboration on Grover's search. The Grover's search, if you recall from last time, how the problem ended up working is as follows. We have a black box oracle, which I called OF, that obfuscates a marked state from the user. So, for example, if we have a state MB in here, then this oracle will end up mapping that to MB plus 1 if M is the marked state. I.e., if it's the thing that you're searching for. So, for example, if you're searching for a number that, or a pair of numbers that when multiplied together equals a target number, M would be that target number, or sorry, N would be that those two integers that you feed in order to be able to check that. So that is what we did, and if you recall, we solved this by building a object called the Grover iterate or Grover walk operator, which is of the form of the product of two reflections. First one reflects about the marked state. The second one ends up reflecting about the initial state that we're in. And by carrying this out m times, so if we apply Wm to a state psi over here, we end up getting that the probability of measuring, of getting the marked state back out is actually equal to cosine squared 2m plus 1, or sorry, sine squared of the arc sine of the square root of the probability of success before you tried amplitude amplification. So what happens with this, the reason why it works, is because these pairs of reflections end up carrying out a rotation in effect, where this is an angle. If this is psi over here, this ends up rotating psi up closer to the marked state M by an angle here of 2 theta, which is why subsequent iterations end up increasing that by 2 theta every time, because, yeah, that's basically just what ends up happening. So, this is how Grover's search works. We're going to generalize this now to a more general case. And this more general case works as follows. Imagine our vector space is split into two categories, okay? What we have is we have one space of inputs that we'll call good, and the other half we'll call bad. And so what we have is our initial state, psi, is always going to have some sort of support on both of these vector spaces. And so without loss of generality, we can always end up writing the state in the form sine theta psi g plus cosine theta psi b, where these are the projection of the state psi on the good and the bad subspaces. We can express this in different language by creating a projector onto the good space, p good, and p bad, because the two projectors have to add up to the identity, meaning every state has to be in the support of either the good or the bad subspace. P bad can be written as identity minus p good. Just like the probability of getting bad is 1 minus the probability of getting good. Okay, so those are our two projectors, and in turn, we can define psi g, which is just the projector of p good acting on psi, divided through by a normalization constant, psi theta. And you can see that both of these are equivalent. And similarly, we would have psi b is equal to identity minus the projection onto good times psi divided through by cosine theta. Okay, so those are the two kind of subspaces that take place for this problem, or the two vectors that we end up having. These are going to end up forming the analog of this vector over here and that one up there. Okay? Similarly, you can see that the probability of getting a good result is just defined to be, well, sine squared theta, because of the fact that this component is the projection onto the bad space. So that is how the probabilities end up working. Let's go through and think about how we actually end up building this quantum state. Let's think about how we're going to go through and reason that we can use or build a very similar walk operator to implement a rotation in this two-dimensional space. So the walk operator that generalizes Grover's search is perhaps not all that surprising. We assume that we begin with an initial state, psi, just like we did previously, and so we have a reflection about the state psi, but we also have now a reflection about the good space, not a single vector, but the entire good space. And we express that as 2 identity minus 2p good. Now, recall that in the case of Grover's search with one marked item, we ended up saying this projector is that. So this is a particular Grover's search with one marked item ends up being a particular case of this where p good is only a projector onto the marked vector. So that's the walk operator. Now, let's go forward and try to understand it. So the first thing that I'd like to do is I'd like to examine what happens when we apply the walk operator on psi g over here. Okay? So if we apply the walk operator on psi g, what we end up getting is we get minus 1, minus 2, psi, identity minus 2, p good, psi g. Now, psi g, by definition, is in the plus one. It's technically in the +1 eigenspace of p good, but what you can think of for that is that this component of the vector is in the good place. What identity minus 2p good does is it flips the sign of everything in the good space. Therefore, this goes to that. And this ends up becoming identity minus 2 psi acting on psi g. Note the lack of the minus sign because the two minus signs cancel. So this, when we expand the product out, is just psi g minus 2 psi g, which, as we noted before, is equal to psi g minus 2 sine theta psi, which we can also express as being equal to psi g minus 2 sine theta psi g plus cosine theta psi b times sine theta. So we can see that when we apply the walk operator on psi g, what we end up with is W maps psi g to the span of psi g and psi b. So a single operation of this walk operator doesn't take us outside of the subspace spanned by the good and the bad projection of the vector. Now, let's take a look similarly at what happens when we operate on the bad vector. So, this is of course equal to negative identity minus twice the projector onto the initial state times the reflection operator that reflects about the good space operating on the state psi b over here. Now, this flips the sign of the good space. However, b is manifestly in the bad space. So what that ends up meaning is that means that it doesn't change the sign at all. And this is equal to negative identity minus 2 projector onto psi multiplied through by the bad vector. Okay. Now this is equal to, of course, negative psi b plus 2 cosine theta psi. And this over here, by going through the exact same expansion argument we did above, this ends up being in the span of psi b and psi g. Ergo, the walk operator preserves a 2D subspace spanned by these two vectors. Wonderful. So, we know the walk operator ends up preserving that space. Now, let's see if we can understand how if it preserves a two-dimensional space, we'd like to be able to understand the form of the walk operator. So in particular, its action on psi g and psi b can be understood by just looking at a two-dimensional matrix that operates on psi g, psi b, and psi b, psi g over here. So in particular, psi g, w, psi g would be equal to a. Okay, well, we've worked out a lot of if we want to figure out this matrix, we can actually just leverage a lot of the work that we've already done. We ended up finding that w psi g is of the following form. W psi g is equal to psi g minus 2 sine theta minus 2 sine theta sine. Oh, like that. Okay, so now if A is just the inner product of this with psi g, which is equal to 1, because the inner product with that and psi g is 1, and the inner product between that and that is sine theta, so that's 1 minus 2 sine squared theta. Now for all you trigonometry nerds out there, this actually can be expressed as cosine 2 theta. All right, so A happens to be cosine 2 theta. Now, let's take a look at what B is. We have B is equal to psi B W psi G. So, give me a sec, my apologies. All right, so now this is, we'll do the exact same thing, but we'll start from this operator over here. What we end up getting when we do that inner product is we end up getting that's equal to minus 1 from this part plus 2 cosine squared theta, which you can see is actually equal to cosine 2 theta. Okay, so that is that. Or, sorry, that isn't cosine 2 theta. This is actually sine 2 theta. Now, continuing this process throughout the rest of the matrix over here, what we end up with is we end up with the fact that the walk operator can actually be expressed as cosine 2 theta. Sorry, this is a minus sine 2 theta, minus sine 2 theta, sine 2 theta, cosine 2 theta, which is equal to e to the negative I y sine, of 2 theta. Or I should say this matrix in this two-dimensional space is the exact same form as this y rotation. And you can see that, again, just using the identity that this is equal to cosine 2 theta times identity minus iy sine 2 theta. Okay, awesome. So that is the walk operator. Now, from this, actually, we have a lot of information. We know that the walk operator over here ends up acting on a vector of the form. We begin with a vector of the form cosine theta sine theta. Oh, sorry. I think it's sine theta, cosine theta, but whatever. So when we carry out this rotation, what we end up doing is we end up basically just increasing the angle by 2 theta. So we end up getting this to map to sine 2m plus 1 theta cosine of 2m plus 1 theta. And this is the action of w to the mth power. So this is just what you would end up getting by rotating this vector through an angle of 2m theta. Okay, so that means that the probability of successfully measuring a vector in good is equal to sine squared, and this is at m iterations, of 2m plus 1 theta. Okay, awesome. And so therefore, if we want to be able to figure out what the value of m is that we should pick, we would like this probability of success ideally to be as close to 100% as we can get. Now sine squared is going to be 1 if the argument is over here, pi by 2. So what we want is we want 2m plus 1 times theta is equal to pi by 2, which implies that 2m plus 1 is equal to pi over 2 theta, which furthermore implies that m is equal to 1/2 pi over 2 theta minus 1. And in general, of course, m has got to be an integer, so we're going to take the floor function of this as our estimate for the number of times that we have to apply this in order to make it work. Now, theta, of course, we can end up writing that as theta is equal to the arc sine of square root of the probability of success at 0 iterations. So we can equivalently also write this as the floor function of 1/2 pi over 2 arc sine of square root probability minus 1. So for example, if we have the magic success probability 1/4, then sine inverse of 1/2 is equal to pi by 6, and then m in this case would end up going to 1. So that's the largest non-trivial angle where we can get 100% success probability. Of course, we could still get it to succeed somewhere in between, but it then becomes probabilistic. Okay, so this basically is how amplitude amplification ends up working. There's a couple of caveats to it. One, how do you select this value of m? Well, there's a couple of different ways that you can do it. The first way is to use this technique called amplitude estimation. And the idea behind amplitude estimation is that what we want to do is we want to be able to figure out what this value of p is as accurately and as quickly as possible. So amplitude estimation gives us a direct path to do this. The way amplitude estimation ends up working is, recall that the walk operator is equivalent to, in this two-dimensional subspace, a y rotation of the form e to the negative I 2 theta y. Okay, so phase estimation, if we applied phase estimation on the walk operator, recall what phase estimation does is it will give you the eigenvalues of the numerator of this up here. So phase estimation will end up giving us, in this case, plus minus 2 theta. Okay, but theta is equal to the arc sine of the square root of the probability. Okay, so what that means is that this walk operator actually is more than just a means in order to be able to monkey with probability distributions. It also gives us a way to kind of transduce between success probability which is what we would see ordinarily when we measure the system, and phase. And that transduction between the two, between changing success probability into phase, is the key to how this ends up working. Because what we're doing is we're taking phase and we're interconverting that back and forth between success probability. And the quadratic difference, in effect, between amplitude and probability is what ends up leading to this quadratic difference between the two, and leads to values of m that end up scaling like 1 over the square root of the probability over here, as opposed to classically, the value of m that you would end up needing would be more like m scales like 1 over the probability in order to be able to get a success. Here, it goes like 1 over square root of the probability in the limit where p is small. But in any case, amplitude estimation ends up doing that. So if you wanted to estimate p in particular, what you would do is you could, if we were doing Fourier-based amplitude or phase estimation, we would have a circuit that ends up looking as follows. We'd have some state. We would feed in a walk operator after doing a bunch of Hadamard transforms to all of this junk. Then we would do a controlled square of the walk operator, going all the way down to w to the 2n minus 1 over here. Okay, then we apply a inverse quantum Fourier transform, and the bit string that ends up coming out over here will encode that rotation angle. All right, great. So now we have an ability to do this, and in particular, by choosing the number of bits up here, n, appropriately, what we can do is we can end up estimating, with high probability, the arc sine of the square root of the probability plus or minus some delta. Okay? And so if we want to be able to learn the probability from this, and let's say this is equal to some value, I'll call it phi for the estimated phase. Okay? So what we end up getting is the arc sine of square root of the probability is equal to, considering the uncertainty, it's going to be phi plus minus delta over here. And therefore, the square root of the probability is equal to sine of 1/2 of phi plus minus delta. And therefore, p is equal to sine squared of 1/2 phi plus minus delta. Okay? Now, just in order to be able to figure out the maximum deviation that we can see, we could end up using Taylor's theorem and say, think about this as the probability as a function of delta minus the probability at absolute value that is less than the maximum derivative with respect to delta of p of delta times delta, which in our case, because this is all order 1, is in order delta. Therefore, the error that we end up getting in the probability ends up going like order delta out of this. So that means that we can learn the probability with order delta error in the phase estimation. And what that implies is because the cost of PE within this error is order 1 over delta, this implies we can learn the probability with order 1 over delta applications of W, or more accurately, the controlled W operator. So we can learn, once we've learned the probability, then we can go from that and figure out exactly what P is over here, which will tell us how many times we'd have to apply M in order to be able to succeed. So that is how you would do it with counting. There's other heuristic approaches that can work and will allow you to find a marked state without knowing the probability. The simplest one is just a random guess. Okay, so what you would do is you would pick first M equals 0. Hey, if you try no work, if you try no iterations and you succeed the first time, great, awesome. But then what you would do is you would try 1, 2, 4, 8, 16, so on and so forth. The idea behind this is that if you begin in a two-dimensional vector space and we have a tiny little angle to begin with, we're going to start rotating slowly through. But because the sequence is expanding, eventually what ends up happening is the phases start rapidly moving all over the unit circle. And once you end up getting to the point where they're spinning around mod 2 pi like crazy in this sequence, then you can see that the average probability of getting a good value is equal to the average value of sine squared of theta, which is actually equal to 1/4. So what that ends up meaning is if we over-rotate, then our success probability is going to be typically something on the order of 1. So what that means is that we only, on average, are going to have to try this 4 steps before we'll end up succeeding once we get into this regime, which ends up leading us to, worst case scenario, a factor of 16 worse. So this procedure of just picking an exponential series and going up like this will, with high probability, end up allowing us to find a state in a good subspace using order 1 over square root of the probability applications of W. Again, if we wanted to do this using classical sampling techniques, we would actually require order 1 over P queries to W in order, or not to W, just random samples before, with high probability, we would end up getting 1 in the good subspace. So that is how amplitude amplification and estimation ends up working. Now, to end this with a concrete example, you might wonder, okay, well, what's something you could do this for? Well, one thing you can do this for is Grover search. For the case of Grover search, we start with a state that has maximum overlap with all the marked items. So if there are n items that we're searching through in quantum search, then the initial probability before we start of guessing the right one is 1 over n. And this amplitude amplification analysis recaptures what we saw last lecture and tells us that we would need 1 over n, square root n applications. However, if there are m items that are good, then the probability that we get a good one is actually m over n. And so the number of repetitions that we're going to need in order to be able to succeed using this, it will be order m over n. So you can see, once we have this tool in place, we can actually solve a Grover search with multiple marked elements just by substitution. And so that's really kind of neat. But also, one thing that I should mention is that for any algorithm that involves stochastic sampling, this technique can be used to be able to provide a quadratic speedup, assuming you can actually apply these reflection operators quantum mechanically. And so what that means is that nearly any randomized algorithm can be accelerated quadratically on a quantum computer through the appropriate use of either amplitude amplification or amplitude estimation. And it's the sheer breadth of applications for this technique that make it so useful. In fact, there are many other quantum algorithms that end up using this as a subroutine because of its breadth. So that is amplitude amplification and estimation in a nutshell. But you might ask, how good is this algorithm? I mean, we saw previously, at least from complexity theoretic arguments, that it's very unlikely that a quantum computer ever could give an exponential speedup in general for the search problem. But what about a quartic speedup? What about a cubic speedup? What about a square root n over log n algorithm? Well, all of those are actually impossible. And square root n, it turns out to be optimal. And so with the remaining part of the lecture, what I'd like to do is I'd like to be able to go through kind of the proof sketch of how the optimality arguments for this can be laid out using a technique known as the polynomial method. So the polynomial method a polynomial method to me is probably the simplest way to prove a direct bound on, or direct lower bound on the query complexity for a function. And in particular, just to be very clear, let's consider a function that ends up mapping the following spaces: 0, 1 to the n to a bit value, to just 0 and 1. So these are the types of functions that we're considering. And what we'd like to be able to do is we'd like to be able to find how many different times this mapping has to be done in order to be able to evaluate the function that we want. So, and part of this evaluation of the function is kind of getting enough information to you kind of uniquely specify what the function is doing. And in order to do this, I'm going to be copying a lingo from Ronald DeWolf's notes, but also Nielsen and Schwang does have a section on the polynomial method, and so I think insights from both of them are actually really quite useful for this. So the way that I'm going to do this is I'm going to define this over here to be the input. I'm going to call that input x over here, which specifies the particular function or the details of the function that's being hidden by the oracle. Okay, and we end up having a bunch of bits representing this going all the way up to xn minus 1. Okay, now I'm going to assume that what we have is that we're modeling our oracles in the following way. That we've got an oracle that queries the ith bit of this input over here. And it outputs it as a bit oracle, meaning that it outputs this bit in the form like that. So these are the resources that we're going to be assuming for the quantum algorithm, and we'd like to be able to get an idea of how many times we have to take a look at these inputs to be able to compute a function. So as a simple example, let's look at the AND function. The AND function takes two values for the bits of the input over here, and then what that will do is that will map to x naught times x1. And so in this case, two queries are needed to evaluate exactly. So in particular, if you, just to give a very concrete example of this, if we wanted to do this on a quantum computer using this oracle OX, what we would do is we'd begin by feeding in 0 up here, and, well, I guess 0 down there, and we would call OX, and this would end up outputting a bit containing x0. Similarly, if we wanted x1, we would query it with 1, put it through OX, and this would end up giving you x1 down here, and the same thing up there. Finally, if we want to be able to compute the AND of the two, then we can just have an extra qubit off to the side and apply a Toffoli gate between the two. So this over here will end up containing a value x0, x1. So here we've computed the function AND using two accesses to OX and an auxiliary unitary. I'll call, yeah. So that is how this ends up working. Now, we can also consider approximating a particular function. It turns out that the AND function can also be approximated using a linear polynomial. So AND of x0 and x1 is approximately equal to 1/3 x0 plus x1. And you'll note that for all values of x0 and x1, that the absolute value of AND tilde, I'll call it for this approximated one, minus the actual AND function, that deviation is less than or equal to 1/3. Okay, so then in this case, what we end up with is we end up with two different notions of equivalence. We have the exact equivalence dictated over here, but we also have this notion of approximate equivalence that I'm discussing here. And both of them are ultimately going to be useful in our discussion. Okay, so in order for us to be able to make some more progress, the other thing that we'd like to note is kind of a canonical form for all T-query algorithms. So all algorithms containing T-queries to OX can be written as the following form: U sub t OX U sub t minus 1 going all the way down to U1 OX U0, acting on some initial state over here that I'll just write as, for our purposes, 0, 0, 0, where this register contains the I, this one over here contains the output for the oracle queries, B, and this is potentially some extra work qubits that we could use in these different unitary transformations that are being put here. So to give some context, here, these unitary operations would be like these Toffoli gates. They're things that that we can intersperse between the oracles that load the input data into the function that we're computing. Okay, so that is basically the form for this. Now, claim this expression up here, star, yields a multilinear polynomial state of the form sum over S contained in 0 going up to n minus 1. So this is a subset of all of these elements over here with some complex values. So these are complex numbers of AS times a expansion of this the bits in this set of the product of that. Okay, and so this is what I mean by a multilinear poly with degree less than or equal to t, where, yeah. Okay, so what do I mean by that? And so in particular, what I end up meaning is that the quantum state that we end up getting out of this is that star maps to, in particular, sum over z in 0, 1 to the n alpha z of x z. Actually, I'm going to call this m prime, because these z's over here are corresponding to the index I, b, as well as these work qubits. So the number of qubits is actually going to be from the total number from this register, and that register. So that's the space, and each of these, in particular, each of these alpha z of x is a degree t polynomial in the input x. Okay. Now the proof is relatively straightforward. The proof follows inductively. Okay, the first case that we need to look at is t equals 0. Now t equals 0 is a really easy case. In the case where t equals 0, no queries are made. Therefore, each alpha z is not a function of x. Therefore, what this implies is that a circuit with an arbitrary unitary acting on 0 yields a state that's of the form alpha z z, which now, because this isn't constrained whatsoever anymore, this is literally any state. And so clearly any state can be written in this particular form. So claim works for t equals 0. So this ends up working for the base case. Now let's go forward to our induction step. So our induction step for this inductive proof is, what we're going to do is we're going to say, okay, well, let's assume it works for capital T. Now the question is, how does the polynomial end up scaling? Well, if we have that, then just by expanding this over here, we can see that the state that we end up getting, which would be ut plus 1 ox ut all the way down to u 0, 0, 0, 0. This, by the induction hypothesis, can always be written in the form ox sum over z alpha z of x z over here, where this is a degree t polynomial. Okay, great. So now actually we can argue about what this sum is going to end up looking like. So just by expanding this over here as taking z equals I b w, we can end up expressing this as the sum over w, sum over I, 1 minus xi ai0w of x plus xi a1 0w of x I 0w plus 1 minus xi ai 1w of x plus xi sorry, this should be a 1, and this should be an ai 0w of x all times I 1w. Okay, so what am I doing here? Well, what I'm doing here is that there's two cases. Either the OX oracle acting on I and B yields I, B exclusive or xi, or it yields IB, depending on the value. Okay, so that's what I'm doing up here. What I'm saying is I'm saying this over here is 0 if xi equals 1. Okay, but this one is 1 if xi equals 1. So these two terms over here are basically doing a piecewise function. One where what we've done is I've flipped the bit over here. So that means that because we flipped a bit when I is equal to 1, we end up getting the coefficient that has the opposite value of b, because that's what happens here. This ends up getting mapped to not b. So good. That's what we end up having. We end up having this particular circuit. However, when we take a look at this expansion, we end up seeing that each of these individual terms is multiplied by worst case scenario, a degree 1 poly. So this was a degree t polynomial by the induction hypothesis. Therefore, this is equal to a degree t plus 1 polynomial. However, the claim was this is a multilinear polynomial. It turns out that the result is also multilinear polynomial because imagine what you had is you had a function of the form, let's say xi xj squared. Well, in our case, the input xj, this is either 0 or 1. In both cases, because 0 squared is equal to 0 and 1 squared is equal to 1, this is the same thing as xi xj. So the result can be written as a multilinear function just because of the fact that all of the inputs are assumed to be either 0 or 1, which are the only two numbers when squared equal themselves. So that is that, and this ends up showing that we end up having a degree t plus 1 polynomial. Flying back out of it. Awesome. So this says that, in general, the quantum state after t queries is a sum over degree t polys in the amplitude, which is basically just what this is saying over here. So, because prob is equal to amplitude squared, this means that the probability distribution is degree 2t. And so, therefore, what we end up getting is that if the resultant probability distribution cannot be accurately approximated by degree 2t polynomial, then you need more than 2t queries. Now, in particular, for the search problem, Beals, Berman, et al. In 98, they end up showing that for the search problem, the probability distribution that we want minus the difference between the ideal search function and some arbitrary probability distribution, if we demand that this difference, the maximum value of this, is less than or equal to 1/3, which is, just think of that as an arbitrary constant that's order 1, then this implies that p of x has degree in theta of square root n. And this implies that if t is, I'm abusing asymptotic notation, is less than or equal to on, meaning, for those of you who are Bachmann-Landau aficionados, if t is in little o, square root n, then the degree of the minimum polynomial is greater than the number of queries, which implies no constant error approximation is possible. And in turn, even under the weakened assumption of the constant error, then this ends up implying that omega square root n, meaning minimally square root n queries are needed to do search. So that's how the polynomial method ends up working. At a high level, the straightforward part is just recognizing that there's a canonical form to the way that all query algorithms end up going. They all have to take their input from a particular subroutine. And then, of course, they're allowed to process that with unitary transformations in between. But that ends up yielding quantum states that end up having functional forms that are particular polynomials of the input bits that specify the function. So what that ends up meaning is that if our degree for the minimum polynomial that's needed to approximate the function closely is less than the value of t that we're picking, then, well, then we're okay. But if it's the other way around, then we could be screwed. So that is how the polynomial method is used. And this is a standard proof technique that's been used in order to be able to show the optimality of Grover's search, but it could also be used for parity and a number of other relatively elementary functions. There's, of course, a whole rich family of lower bound methods that end up existing for quantum query complexity. And this is one of the things that makes quantum query complexity so awesome. It's that, well, with time complexity, which really is probably the thing that we actually really wanted to know about, there's just so many open questions about it. We don't know even whether or not a quantum computer can be simulated in polynomial time by a classical computer. But we are capable of using this in order to be able to prove lower bounds on a number of quantum oracle queries needed. And so what this ends up implying is this implies that since classically, we saw this earlier, we need omega square root, or sorry, we need omega n classical queries. Quantumly, this shows that theta square root n is possible. And because of the matching lower bound, this also implies that this is optimal. So, what that ends up meaning is that this ends up leading to a provable gap between what we're capable of doing for a wide range of interesting problems using quantum computers. In contrast, the behavior, the gap that we ended up seeing previously with the Deutsch-Jozsa algorithm ended up only being for deterministic algorithms, not ones where we were allowed to fail with some fixed probability. But also, that application for the Deutsch-Jozsa algorithm, where we were just trying to figure out whether a function was constant or balanced, that application, it's really useless. But this over here, it's used all over the place within quantum algorithms. In fact, amplitude amplification and Grover's search is one of the fundamental tools that most modern quantum algorithms end up using, at least to some extent. If not that, then they'll use the quantum walk algorithms that generalize this even further. But I digress. So that is basically how we can answer some of these questions about what the gulf is between quantum and classical just by taking a look at approximating polynomials and using that to bound a number of queries. So thank you very much for bearing with me, and next time, we're going to be going into some new stuff. Thanks a lot. See you next time.